So, um, you guys, anyone on the travel to Italy? You went to Pisa, right? Okay, so the story is the famous myth story about Galileo dropping the large cannonball and the small cannonball off the Leaning Tower of Pisa. I don't know if it was leaning quite as dramatically back then. And Aristotle, from early civilization over 2,000 years ago, would have said that the cannonball that was 10 times more massive, would actually land 10 times earlier than the lighter one. And no one bothered to actually check it out. Hard to believe, actually. So the story is that Galileo actually went up and dropped it off and said, yeah, Aristotle, you're wrong. So my good friend Jake Rampton, who many of you know, let's just explain this then. Why does it work that way? Free fall explain. Galileo showed that falling objects accelerate equally. What is the acceleration? 9.8 meters per second squared. Well, by the way, some of you still don't understand what acceleration is. I marked those tests. Some of you still think that when the acceleration is constant, that means that the acceleration changes. And I'm like, yeah, no, that's two different things, right? So we'll have to work on that. This is strictly true if air resistance is negligible. What does the word negligible mean? It means it doesn't matter. It's so small that it doesn't matter. That is if the objects are in free fall. It is approximately true, or almost true, when air resistance is very small compared with the mass falling on it. For example, the 10-kilogram cannonball and a 1-kilogram stone, drop them in an elevated position at the same time, will fall together and strike the ground at practically the same time. This experiment, said to be done by Galileo from the Leaning Tower of Pisa, demolished the Aristotelian idea that an object that weighs 10 times as much as another should fall 10 times faster than the lighter object. Galileo's experiment and many others showed the same result were convincing, but Galileo couldn't say why the acceleration is equal. The explanation is a straightforward application of Newton's second law, and is the topic of the cartoon Backyard Physics, which is on the back side. We'll get to that right away. Okay? So Newton's second law is which one? The F equals ma. So how does Jake Rampton on top of silos relate to Newton's second law? F equals ma. Remember, the A is constant 9.8 for the Pepsi bottle or for the 2-liter. Which one has bigger mass? The milk jug, right? So right, one's got a bigger mass, but the accelerations, whoops, why did I do that? But the accelerations are the same size. So what does that mean over here? The forces have to change, right? The forces have to change, exactly. Second paragraph. Recall that mass, a quantity of matter, and weight, the force due to gravity, are proportional. A 2-kilogram bag of nails weighs twice as much as a 1-kilogram bag of nails. Although yesterday we did prove that a pound of feathers has the same weight as a pound of bricks, right? Don't get caught up with that. The 2-kilogram bag of nails weighs twice as much as the 1-kilogram bag of nails. So a 10-kilogram cannonball experiences 10 times as much force as a 1-kilogram stone. The followers of Aristotle believed that the cannonball should accelerate at a rate 10 times that of the stone, because they considered only the cannonball's 10 times greater weight. However, Newton's second law tells us to consider the mass as well. A little thought will show that 10 times as much force acting on 10 times as much mass produces the same acceleration as the smaller force acting on the smaller. In symbolic notation, and you've got it right there, I'm going to rewrite it. If you've got a little tiny force, because it doesn't have much mass, and a little tiny mass, well, the ratios are the same. And what is that ratio, F over m? It's acceleration, 9.8. Where F stands for the force acting on the cannonball, and m stands for the corresponding large mass of the cannonball. The small f and m stand for the smaller weight, smaller mass of the stone. We see that the ratio of weights to mass is the same for these or any other objects. All freely falling objects undergo the same acceleration at the same place on Earth. Now, what does that mean? The same place on Earth. What does that imply? Are there different places on Earth where gravity is different? Yeah, it's true, actually, right? The higher up you go, the less gravity is, to a small extent. And there are some weird anomalies. They're not really sure. There's some weird places. But for the most part, it's 9.8. It's 9.8 means as much as that. Small difference. In chapter 2, we introduced the symbol G for the acceleration. We can show the same result with numerical values, or quantitatively. Remember those things from yesterday's outcomes, qualitative and quantitative? The weight of a 1 kilogram stone is 9.8 newtons at Earth's surface. The weight of a 10 kilogram cannonball is 98 newtons at Earth's surface. The force acting on a falling object is the force due to gravity, the object's weight. Using Newton's second law, the acceleration of the stone is 9.8 over 1, or 9.8 meters per second squared, which is g. And for the cannonball, 98 newtons over 10 kilograms. Once again, 9.8. In the famous coin and feather in a vacuum tube demonstration discussed in chapter 2, I didn't talk about that, but if you put a coin and a feather in a tube, and I actually have one somewhere, look for it. You put a coin and a feather in a tube and you take all the air out, they should fall at the same rate. Do you believe that? I think most people do, but they're a little shocked when they see it. It doesn't actually work real well because it's hard to get all the air out of that tube. In the famous coin and feather in a vacuum tube demonstration discussed in chapter 2, the reason for the equal accelerations was not discussed. Now we know that both freely falling objects fall with the same acceleration because the net force on each object is only its weight, and the ratio of weight to mass is the same for both. Okay, there's a question at the bottom, and I think, let me just see. No, that one here. Go get a clicker. The question is, if you were on the moon and you dropped a hammer and a feather from the same elevation at the same time, would they strike the surface of the moon at the same instant? Because if you do that on Earth, I don't have a feather, but I got a hammer, and I got what appears to be a clean Kleenex. I'm going to do it. I'm gonna. Are they going to land at the same time? I'm not going to miss it. Are you sure? No, I'm not actually. What do you think? Get someplace where you can see, because, like, you know, you can see? You can see the ground? Not even close. What's going on? Not even close. Aristotle was not right. Large surface area, smaller, really light, not so much light, heavy. Air resistance, exactly. Now, I'm still waiting. Come on, you guys. But remember, the question is on the moon. Did you guys talk to the spoon? No? Now we got the, it's not one at a time? Oh, really? Okay, well, we'll come back to it. Okay. Should we do the other questions? Okay, let's try this one then. Alrighty, so you've had a nice little break there. You've all checked your phone, right? Your stocks haven't changed too much in the last 30 seconds, so now it's time to listen to me. What do you mean I lied? Wow, really? Okay, well, let's have a look at the first one here. Okay, so the question is, you saw me demonstrate here, but that's on Earth. In case you hadn't noticed, this isn't the moon. I'm not Ms. Frizzle. This is not the magic school bus. Although if we had a magic school bus, that would be a fantastic way to learn science. If you were on the moon and dropped a hammer and feather at the same elevation at the same time, would they strike the surface of the moon at the same instant? And the answer is, of course, well, I shouldn't say of course, because the answer is, yeah. How come it didn't work here? Air resistance. You are familiar that there's no air on the moon, right? That's why they wear the big helmets, right? Now, if only there was some way that we could confirm this. Well, they fall slower because the acceleration on the moon is only 1.6. Now, Nowadays, in 2016, can you fake that with a computer? Yeah. That was 1969 or 1970. You've got more computing power in your little clicker thingy there than those guys had going to the moon. They cannot fake that back then. If they were to fake it back then, it would be like, you know, those old movies where the guy's driving the car and there's the movie screen in behind and they're not bounced or anything, right? That kind of fake, right? Yeah, they didn't fake it. Okay, let's go to the cartoon on the backside. Okay, let's go to the cartoon on the backside. Okay, I will have to warn you, this is not a cartoon that's funny. Remember the videos I showed you with the guy with the really bad jeans, right? Remember that? Yeah, you do. Right? Remember kind of weird professor dude, had the acid wash jeans on, you guys all make fun of him? Okay, he's also a cartoonist. He knows what he's doing though, he's an award-winning teacher. So, anyways, backyard physics, right? This probably never happens in your backyard. So the lady is asking out the window, she says to the two kids, if I drop the bag of clothespins and the single pin at the same time, which will fall to the ground first? Now, what would Aristotle say? Aristotle would say the bag. Galileo would say same time, right? So the one kid says, that's easy, the bag of clothespins is heavier. Is that true? That's true. Which means gravity pulls on it with more force. Is that true? Yes. So the bag of pins will accelerate more and hit the ground first. That part, this guy scratches his head, says physics, 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 and says not true. The bag of clothespins has more mass, which is to say it has more inertia. It will be less responsive to gravity and lag behind the single pin. In other words, the single pin will fall first. And he says, well, that's what he says. So the single pin will hit the ground first, right? And she drops them. And of course, they land at the same time. And then she says, she explains that since the bag has both a greater weight and a greater inertia, one offsets the other. The ratio is the same. Big weight over big mass is equal to little tiny weight over little tiny mass is equal to g. The accelerations are. Funny stuff, right? That's a chuckle and a half. He didn't make his living right drawing cartoons, put it that way. Okay, next page. Falling and air resistance. Okay, this is 5.7. The feather and coin fall with equal accelerations in a vacuum, but quite unequally in the presence of air. When air is let into the glass tube and is again inverted and held upright, the coin falls quickly while the feather flies to the bottom, just like when I drop the Kleenex in the hammer. Right? You guys are listening now, right? Here's the explanation part. Don't talk, listen. Air resistance diminishes the net forces acting on the object. The net force decreases a tiny bit for the coin and a lot for the feather. The downward acceleration for the feather is very brief because the air resistance builds up quickly and counteracts its tiny weight. The feather does not have to fall very long or very fast for this to happen. When the air resistance on the feather equals the weight of the feather, the net force is 0 and no further acceleration occurs. So the air resistance builds up, and because it equals the weight force, those forces are balanced, and you get it no longer accelerating. I'm going to insert a blank page right here, and in that little spot right there where it looks like it's part of, there's a little blank spot, I want you to do this. Weight force, and I'm going to say FAIR, air resistance. And when they are equal, that means the net force is 0, which means the acceleration is 0. I realize I've asked you to write quite a bit in that little space. Right? When the forces are equal, why don't you just stay in bed and watch stuff at home, Alex? For both of us. If we're concerned with direction, which is down, acceleration terminates, the feather has reached its terminal speed. If we're concerned with direction, which is down for falling object, we say the feather has reached its terminal velocity. It's in bold for a reason. It's a word you need to know. It's even on the list of outcomes, I think. Terminal velocity. What does terminal mean? Final, right? When someone has a terminal illness, it means that's the last one they're having. What it means, right? Is that one of the outcomes? I think so. Let's just go here. I gave it to you yesterday, right? Describe terminal velocity qualitatively and quantitatively. Okay? So you need to be able to explain when terminal velocity occurs. It's when the air resistance is equal to the gravitational force, and therefore there is a net force of zero. There is a zero acceleration, and the object continues to fall at the same rate. Now, what kind of objects does have a really small terminal velocity? Already at terminal velocity. How come? Doesn't have much weight, right? The weight force on it is very, very tiny. It has a lot of surface area. So it literally reaches terminal velocity like now. Instantaneously, right? Which is why it falls at a very small rate of speed. The hammer, on the other hand, heavy, large force, needs a long time for the air resistance to build up, right? The faster it goes, the more air resistance. Have you ever stuck your hand out the window of the car going down Main Street? It's a lot of fun, right? Well, I've seen you doing it. Right? You've probably done this one too. Yeah, that's even more fun, right? But if you do it down Main Street, you know, you can wait, no problem, right? You ever done it down the highway? Torn rotator cuff, right? Well, not fast I got, right? But your hand will go back though, right? How come? You're going faster, greater air resistance, right? Your air resistance depends upon your speed. Okay. Second paragraph there, underneath where the little break is. Air resistance does not have as much effect on the coin. At slow speeds, the force of air resistance is very small compared with the weight of the coin, and its acceleration is only slightly less than the acceleration of free fall, the g. The coin might have to fall for several seconds before its speed is great enough for air resistance to equal and cancel its weight. Its speed at this point, perhaps as much as 200 kilometers an hour, would no longer increase. The coin reaches its terminal speed. The terminal speed for a skydiver varies from about 150 to 200 kilometers an hour, depending on the weight and the orientation of the body. A heavier person will attain a greater terminal speed than a lighter person. The greater weight is more effective in plowing through the air. Body orientation also makes a difference. More air is encountered when the body is spread out and the surface area is increased, like that of a flying squirrel. Terminal speed can be controlled by variations in body orientation. A heavy skydiver and a light skydiver can remain in close proximity to each other if the heavy person spreads out like a flying squirrel, while the light person falls head or feet first. Parachute greatly increases air resistance and cuts the terminal speed down to 15 to 25 kilometers an hour, slow enough for a safe landing. Okay, so imagine this. Put this page down. Okay, so I just go on a plane and I jump out. I'm not going to do that. Okay, and I got my parachute. I increase my speed. I fall, faster, and then I pull the cord. What happens to me? Do I go flying up into the air? You see that all the time in videos, don't you? But like when they pull the cord, the person goes. That's because the camera keeps falling, right? Oh, you'd be surprised how many people think the person actually goes up in the air. Now, do they slow down? Yes, they do. If I go really high and fall, and I reach terminal velocity of say like, I don't know, what they say? 200 kilometers an hour, and then I pull the ripcord out with the parachute, how do I get to 15? Well, I slow down, right? Yeah, the whole idea of the parachute is what? Slow you down. When you hit the ground, your terminal speed is like 15. You know the old saying about it's not the speed that will tell you to land, right? I think same idea. Okay. If you hold a baseball I'm at the bottom third. If you hold a baseball and a tennis ball at arm's length and release them at the same time, you'll see them strike the floor at the same time. But if you drop them from the top of the building, you'll notice that the heavier baseball will strike the ground first. Baseball, even if I do this, where's my tennis ball? Oh, perfect, I got a football here. But they're different size, aren't they? It has to be two things that are same size. Will this work? Will you notice the difference here, do you think? Let's try it. I've never done this one. Will you notice the difference? A little? I gotta make sure they're the same height. I always think of my old physics teacher when I do this. I'm not going to fall. Don't tell my doctor. Why is this still here? It's for hanging stuff. Yeah, that one I need. Oh yeah, there's one there. Check that. Okay. What do you think? Why would this be any different?
Because there's more time to gather air.
Exactly. So do you think this one's going to land later? Renee's worried about me, I can tell. No, I was just sleeping. Is there a difference?
Yeah.
I think there was. Ed? You want me to jump down? Yeah. I'm going to jump down. I may be stupid, but I'm not great. Eh? Okay. So, I'm going to read that paragraph again because I don't remember where I left off. If you hold a baseball and tennis ball at arm's length and release them at the same time, I read about here, about 2/3 of the way down. If you hold a baseball and a tennis ball at arm's length and release them at the same time, you'll see them strike the floor at the same time. But if you drop them from the top of the building, you'll notice the heavier baseball strikes the ground first. This is due to the buildup of air resistance at higher speeds, like the parachutes in the question. At low speeds, air resistance is often negligible, but at high speeds, it can make quite a difference. The effect of air resistance is more pronounced on the lighter tennis ball than on the heavier baseball, so the acceleration of fall is less for the tennis ball. The tennis ball behaves more like a parachute than the baseball does. Last paragraph. When Galileo reportedly dropped the objects at different weights in the Leaning Tower of Pisa, the heavier objects did get to the ground first. However, the time difference was only a split second, rather than the pronounced time difference expected by the fall of Aristotle. Aristotle's followers would have said it would have been 10 times. Clearly obvious. It was just like boom, boom. The behavior of falling objects was never really understood until Isaac Newton announced the second law of motion. Isaac Newton truly changed our way of seeing the world and has a unit named after him. Good for him. Okay. Oh yeah, this is my favorite one. Backside. If you drop a sheet of paper and a book side by side, the book will fall faster because of its greater weight relative to air resistance. If you place the paper against the bottom, so okay, I'm going to stop reading because I think the answer's given away. Let me get a look. We use this one. And I use this paper. Both the same size. There we go. I need bigger ones. Okay. Book, paper. What will happen when I drop them at the same time? Ready? Easy question. What's going to happen? What's going to fall first? I thought we've been saying all along that they fall at the same rate. No? Which one reaches terminal velocity first? Paper. How come? Low weight. Same, basically the same surface area, right? When I did it in that room, Mr. George always used to say, "Break, what are you doing up there?" Okay, now. Let's move. I'm going to put the paper on top. What's the paper going to do? This is not an easy question. Well, it's either going to stay with the book, or it's going to separate. Wait, Brady? Oh, Tyler wants to answer? Do you think they're going to separate? The book's just going to flutter? What did I say? That'd be weird, eh? If it's not, wouldn't that be? Man, I gotta figure out how to do that. Just to freak kids out. They stay together. I'll do it again. Stand up if you want to see it. What happens? How come? Yeah, the book pushes the air out of the way, right? It's basically the paper is falling in a vacuum, right? People do this all the time on the highway. It's kind of dangerous. People pull in behind big semis and do what? They drive behind them, right? It's kind of dangerous, but it blocks the air resistance, good for your gas mileage. They do it in biking all the time. The guy in front blocking all the wind, right? People in behind not getting as tired. Okay, now smart people.
The book's gonna flutter.
Does the book do this because the paper's on the bottom? I gotta figure out how to do it. Just 1 year. Only I can make the book flutter. Okay, 2 identical pieces of paper, same amount of ink on them. They're identical. Based on air currents, really? Right? Like basically the same time. Same piece of paper. Nothing up my sleeve. Renee?
Yeah?
Which one's going to land first?
That one. Yep.
How come? Same piece of paper.
Area.
Smaller surface area. Okay, so now let's go through the questions that you answered. Do you want to change your answers, maybe? Too late, right? Correct answer is A. Let's read the question. Listen, you guys. These are the questions that are going to be on the test. You got to understand this. I know you want to visit. I get that. If a heavier person and a light person open their parachutes together at the same altitude and each wears the same size parachute, who will reach the ground first? The heavier person will. Here's the explanation. The heavy person will reach the ground first. Like a feather, the light person reaches terminal velocity speed sooner, while the heavy person continues to accelerate until a greater terminal speed is reached. The heavy person moves ahead of the light person, and the separation continues to increase as they descend, because the heavy person is going faster the whole time, right? All of this same time stuff is only true when what? When air resistance is negligible. And when is air resistance negligible? When you're on the moon, or it's a really small distance. Right? It's the really small distance that matters. We're talking about people jumping out of airplanes. Right? Air resistance matters. If the force of air resistance is the same for a falling baseball and a falling tennis ball, which one will have the greater acceleration? The baseball. A. Not easy. These are not easy questions. That's why I'm going to leave these answers up when I post them. Don't say the same. It's the truth. The air resistance may be the same for each, but that doesn't mean that the net force is the same for each, or that the ratio of net force to mass is the same for each. The heavier baseball has the greater net force, and greater net force per mass, just as the heavier parachute is previously considered. Convince yourself of this by considering the upper limit of air resistance, that is, when air resistance is equal to the weight of the tennis ball. What would the tennis ball's acceleration be? It would be 0. But when this amount of air resistance acts on the heavier baseball, do you see that the baseball still accelerates? And with more thought, do you see that the baseball has the greater acceleration even when the air resistance is less than the weight of the tennis ball? Hard stuff, that is like top of your necessary understanding. I'm not expecting every person to get that one. I'm going to leave it up there for you guys to think about on your own.